Today, when it comes to calculus and differentiation, there's a few things that we work with and that is contingent in this topic. And that includes functions, tangents, stationary points, x-intercepts, y-intercepts, point of inflection, derivative, second derivative, and the gradient of the tangent. When we work with functions, specifically, we work with local stationary points. There are points on the graph which will be a maximum or a minimum value. It is not necessarily for the entire function, but at a specific place. This is called the local or relative maximum or minimum turning point. The maximum or minimum for all the input values x are called the global or the absolute maximum or minimum. If you look at the picture that I will reveal shortly, the graph of a cubic function, the figures are used to explain the concept of local and global maximum or minimum. In a cubic function, we would generally have a local maximum and a local minimum. But in a fourth degree function, we will have an absolute maximum because there will be two maximum values, or it could be two minimum values if it's a negative function. In this case, the positive function shows an absolute maximum and a local maximum. So then we get a local minimum. If this was flipped over, then we would have had a absolute minimum, a local minimum, and a local maximum value, because it will only have had one maximum value. There is only one global absolute maximum and or a global or absolute minimum turning point, but there can be more than one local minimum or maximum turning point. If a cubic function has only one stationary point, then it is a point of inflection. I think we all have a fair knowledge of graphs, and for this exercise I would use the function ax cubed plus bx squared plus cx plus d to illustrate certain properties of functions. So if I look at this straight line function where I have the d value, which is my y-intercept value, then I will have different values according to the information that is displayed. So if d is equal to minus 3, it will cut at minus 3. If d is equal to any value, it will cut along, and everywhere on that line will be that particular value of d. When I add the c value, which is my gradient for my straight line graph, y is equal to mx plus c, the c in this instance is my linear x value with a y-intercept. So I can see that this graph changes the different values according to the gradient. It changes the slope of the line. It changes also the y-intercept as we go along. So now I increase with the b value being b squared. I will find that I'm no longer working with a linear, but I'm working with a quadratic function. And this function's gradient and slope will change according to the information that is available. So my b value, as that becomes a negative value, my c, I just want to pause quickly with the d value and show how this graph will change if my values changes. So when we look at the b value, change c to 0, we will see different values taking place. D at 0, just so that we can see an effect, specific effect. Here B has got positive values. Go to the A value, activate A. So now we see there's another leg taking place on this particular graph. We add the C value now. And see the effect of this graph when the C value is added. Add the D value now. Move the opposite direction there. The y value of the function at x is equal to a is greater or equal to any y value for that interval. The function of a is therefore the highest point on the graph for that interval. The graph has a local or relative maximum at x is equal to a. The function of a is greater or equal to the function of x for all x in the interval. The y value of the function at x is equal to b is the highest y value for the entire function. F of b is therefore the highest point on the graph for the entire function. The graph has an absolute maximum at x is equal to b. Therefore, the function of b is greater than or equal to the function of x for all x for the entire function. To find the x values of the local maximum or minimum turning point, solve the derivative of the function of x and equate it to 0. To find the x value of the point of inflection, solve f double dash x, equate it to 0 and solve for x. Right, to conclude into sketching of a cubic function, y is equal to the function of x is equal to ax cubed plus bx squared plus cx plus d. We saw the motion that the graph takes when values are changed. If a is greater than 0, it means a is positive. The graph will take the following motion, or even as that one. If a is less than 0, meaning a is negative, then the graph will first go in a negative direction, make a turn and go to the top and come back and continue in a negative direction. Or the graph can merely take a motion as that. When we want to calculate the y-intercept, we make x equal to 0. When we want to calculate the x-intercepts, we let y be equal to 0 and solve for x. For the local stationary points, a cubic graph with 2 turning points has a local maximum or a local minimum. How do we calculate these points? First, we have to find f prime x. So that means we have to find the derivative of the function. Once we have the derivative, we equate the derivative to 0 and we solve for x. This will tell me at which x values I will have my two stationary points. The gradient at the stationary points is equal to 0, and we have that understanding that if I have a function, the gradient is equal to 0 because that line runs parallel to the x-axis, either on this side or on that side where it makes the other turning point. So that means the stationary point is the point where that, if a tangent is drawn to the function, it will be parallel to the x-axis. Once we calculated the two x values, we calculate the corresponding y value by substituting it into the original function. We substitute that x value into the original function. Also, remember that not all cubic graphs will have turning points. Some of them will only have a point of inflection. To find the x value of the point of inflection, we solve f double dash x, meaning the second derivative. We calculate the derivative of the function, and then we calculate the derivative of that answer. Once we have that, we equate the second derivative to 0, and we will find the x value for the point of inflection. We take that value and substitute it into the original function, into f of x, to calculate the corresponding y value for that point of inflection. To find the nature of the turning points, we can look at the following table. And we can conclude that when f dash x is greater than 0, meaning where the derivative is greater than 0, the gradient is positive and the function will be increasing. Where the derivative is smaller than 0, the gradient is negative and the function is decreasing. Now we'll quickly see when a is positive, what happens with the graph. I can see when all my other values is 0, and I increase these values, what happens to the function. X is negative. When a is negative, I can see the values of this function. I want to get to a positive point. So if there is also a b value, and you can look here, the b value and then the c value and then the d value will be added at the back. What happens to the graph when a b value is added? What happens to the graph when a c value is added to the equation? What happens to the graph when a d value is added to this equation? I can see the movement of the graph in different aspects and ratios depending the information that I have at my disposal. Thank you for watching this video. We will see you in the next one. If you liked it, please like, subscribe and turn on your notifications to enable yourself to be notified automatically if new videos is uploaded. Thank you for watching. See you in the next one.